Great. My name is Hamid Mumin. I'm a professor in the Geology department here at Brandon University, and it's my research team that's working with Cypher Environmental, on the road stabilization project. So what we'll do today is give you a brief introduction to what we're doing, and we'll take you through a road build and give you a rough idea of how and why this particular process works.
But we pride ourselves in doing innovative research and research that benefits the community. And Hamid's research on road stabilization is something that is a broad benefit, not only to rural Manitoba, but really worldwide. There's been interest from this across the globe. And Hamid, I think, has had 7 international delegations come to see what he and his team are doing. So this is an example of a project that really benefits communities. And you're all rural people. I'm a rural person. I lived in a farm outside Newdale for several years. I know what gravel roads are like in the summer, where you're driving behind something and you can't see anything but a cloud of dust, and then you get out of your vehicle and you wonder why it's so brown. So any of these projects that help stabilize roads really benefit our community.
You know, we've been in this business a long time. You know, we figured, instead of hearing it from us, it was a great idea to get you all together and hear from some of our research partners. We're really happy with the relationship we've had with Dr. Mumin and his team and the Brandon University as a whole. Like Heather pointed out, we've had several international delegations here as well. I've personally been to 40 countries introducing these technologies and building roads. We work with municipal clients, we work with multinational mining companies where they have 400-ton haul trucks driving on the roads we build, and it's just really cool to be able to actually understand our own products more through the research that Dr. Mumin and his team are doing here right in our own backyard. We're based out of Winnipeg.
I want to give you a little bit of science, but not a lot, but just enough so you can get a feel for why it is we can use the clays and the type of clays we use to actually cause these gravel roads to bind up very solidly and end up with durable roads. But before we get started, I'm going to pass around these clay pucks. This is Penner-Pit clay. So this is the clay that we used in the stabilization of the roads we built in the RM of Cornwallis. And what you see here, I'm going to pass this around too. They're just clay balls here, soft pipe. It's the same material. It's both Penner-Pit clay. This one is before it's been treated. These ones have been treated and compacted. The success of the roads that we build is a combination of a number of things. It's related to the engineering and the test work. There's the materials and the input, and then there's the construction. And all play an important role in it. So I'll pass this around and you can just see, and then we'll come back to these during the presentation. So you all know the problems. I can skip this. I don't have to tell you that rural gravel roads fall apart very quickly, and you get all kinds of problems happening. And in addition to that, there are all the environmental problems associated with things like the airborne dust, chloride degradations that take place when you're using chlorides to stabilize roads. But there are also construction issues, and one of the construction issues I want to point out to you is that you may not be aware of, but what we call clays, even when you put that clay binding in your 8 base at 8%, it's actually not true clay. That minus 200 mesh fraction contains some clay, but most of what's in there is typically non-cohesive silt. Very fine particles that don't help, and all they do is contribute to that massive dust cloud that we're dealing with. So our project goals are, we want to stabilize these unpaved road surfaces by using local materials, so standard equipment and very simple technology, so it's cheap and efficient and cost effective. Maintenance, reduce it to a minimum, and we want to make roads that are environmentally sustainable, like no environmental negative impacts, and also build safer roads. So current applications, as we've mentioned and Todd has mentioned, this or a version of this technique has been applied to things like mine haul roads. In fact, in situ, okay, where the ground has a natural high clay content, and that is typical of areas like tropical, subtropical, non-glaciated, and arid environments, okay? You have a lot of clay in your soils right at surface, so you can basically scarify the material and then in situ apply the product, recompact it in the proper way, and away you go. You produce really good roads. And here's an example of a Cypher road using the EarthZyme product from Cypher at the Shenhua coal mine in China, and you can see the size of the trucks that they run on these roads. And their savings, and there are documentation of that, are in terms of fuel, wear and tear on the trucks, removal of maintenance, elimination of the dust problems is huge for the appropriate applications like this. Okay, so this was not done, has never been done on municipal roads in Canada. We have a problem here because we don't have clays. It's a challenge, but there's also an opportunity in that, and that this gives us the opportunity to engineer the whole process from beginning to end. Finding the right clays, mixing it with the right aggregate mix. Okay, so and that gives us an opportunity to engineer the whole process. And if you can do it and it works so well on an in situ basis, you know, my thesis here is that we can do it a heck of a lot better even when we have full control over the materials and the whole process from beginning to end. So that's what we're working towards. Okay, now I'm going to tell you a little bit about clay and why clay can be used as a good binding agent. Now, clays, okay, are very, very tiny plate-like materials, plate-like minerals. They're typically less than about 5 microns in size. And there's a few examples of different clays that I've shown you here. Kaolin is an example of a clay which is relatively inert. Okay? It's non-cohesive. So if you have clay, which is kaolin, it may contribute to your dust, okay, and not do a whole lot else. On the other hand, there are clays that are highly reactive, like montmorillonite and illite, and they're known as cohesive clays. In other words, they can be sticky, very sticky and gumbo. And these are the ones that are known also as swelling clays because they absorb water like crazy and they expand and they contract and expand and contract as they dry and swell. So they're normally considered the last thing on earth you ever want to use as a construction material or a base or something that you could walk on or run a vehicle on. But this is the exact material we use, and I'll explain why that is. Okay? Clays absorb water like crazy, especially these cohesive reactive clays. And the reason is, there's 2 reasons. One is that water is a polar molecule. Okay? It has positive ends to it and it has negative. So the hydrogen, 2 hydrogen atoms are positively charged, and that leaves the oxygen with a negative charge. It's electrostatic charges. They stick to each other. So positive bonds to negative. It's just like, and it's exactly the same kind of electrostatic charge if you took a balloon and you rubbed it on your jacket and you stuck it on the wall, okay? That's the kind of bonding energy that exists in these kind of materials. Now, if you wonder, okay, what's the strength of water bonding to water? Okay, so take some water, okay, remove a little bit of heat from the water, and then it sets up and bonds very rigidly, okay, into a mineral that we know as ice. Okay, so how strong is that ice bond? Well, you all know, okay, but that gives you a feeling for the type and the strength of the electrostatic attractions that exist. Now, in clays, okay, clays are strange minerals. They're different than any other mineral in that they, when they form, they're not electrically neutral. Okay, which is in nature is something that can't happen, but it happens with clays for very specific reasons, which I won't get into. But they end up with excess negative charges, which distribute on the surface of these platy minerals. These negative charges bond to the positive ends of water molecules. And that's why they suck water in and they hold water so well. So you end up with, when you have a reactive clay, like montmorillonite, okay, a swelling clay, you end up with clay, water, clay, water, clay, so it loses all its strength, it swells, and creates a real problem. But the interesting thing, the irony of it all is that in this problem is our solution, okay? And this is the way the solution works, okay? Is that in the normal clay, which is full of water, okay, we add the product, the EarthZyme product, and what it does is it helps get rid of the water, okay, and replace the water with these positive cations, and that is just like cut off there. That says aluminum, sodium, iron, magnesium, potassium, calcium, etc. They're positive ions. So if we get positive ions in between the clay, we produce a semi-permanent bond. So clay, metal ion, clay metal ions, clay metal ions, and so on. What that does is causes the clays to cement up and bond to each other, and helps prevent water from getting back into the system and then destroying everything. So the extent to which we can make this process happen, okay, is directly comparable to the strength of bonding and the permanency of bonding that results from the whole process. Okay, so hence, reactive clays, that is, can be used as one component of the bonding or gluing agent. The other component, as mentioned, are the positive cations, which are materials that exist naturally everywhere in nature, and we've had more of these as well. The structural framework, okay, is then provided by your typical A base, road base, but an A base that has a very good particle size distribution. So here's an example of a good particle size distribution, where you went from roughly -3/4 all the way down to finer and finer particles, mix them all together, and then you have this -200 mesh, or this focal engineered clay size fraction, okay? Except that in the roads that we build, the EarthZyme roads, the proportion of the fines, okay, would be about 1/3 of the total weight, okay, percent of the entire mix. So we had a very high clay content, whereas normally you're used to putting in about 8%, okay, of whatever clay or fine material that they may come up with. Okay, now we're going to increase it to about roughly 25%, a quarter to 1/3 of the entire volume, or let's say weight percent of the road material that we're making. Okay, but the other thing about the clay is it has to contain the right type of clays, and that's very important in this. Okay, so in Manitoba, we have the right clays. Well, clay deposits in Manitoba are very widespread. Okay, they were deposited at the base of Lake Agassiz. Lake Agassiz was the giant lake that covered the entire province and beyond, at the foot of the retreating ice sheet, okay, after the last glaciation. So pretty much everywhere down there, underneath, we'll find these, what we call glacial or custrian deposits. And they're mixes of clay and silt, okay? And in the silt, various typical minerals like quartz and feldspars and carbonates, and then various clay minerals. Some are reactive and some are not, okay? The clay mineral content in the Brownon area, okay, the clays ranges from less than 1%, okay, to greater than 30%. And that's the clay content of the clay, okay? What we normally think of as clay may not have any actual clay minerals in it, maybe just fine silts. So we have to be careful about that. We've tested pits north of Alexander, and 98% -200 mesh fines, and 0 in terms of its cohesiveness, okay? So that's what this is, the plasticity index, which we have to determine, is its cohesiveness or the binding energy of the clays. That ranges from nothing to greater than 25. For our purposes, we need a plasticity index of 8 or greater, and for comfort, I like to see 10 or better, but 8 or better works just fine, and along with the high percentage of the clay fraction of fines that we use. This is an example, this is from our own SEM lab, of hennerkit clay, okay, after it's been treated, okay. So here's the same type of clay, montmorillonite clay. You can see it's very flaky particles and set up in like a flocculated, like a kind of texture, set up like a house of cards. Because of the negative charge, the clay flakes repel each other, and they're happy to set up like this and absorb all kinds of water and so on and so forth. Okay, after treating, this is again montmorillonite with badilite clays, and you can see that we're getting the clay particles to cement up, okay, in a much more solid fashion than what you see here. So, and this is a result of two things: it's the product and compaction that's applied. Okay, so the practical, okay, technical side of this is as important as the chemical, okay, part. So at the university here, we do a lot of testing. We do, I'm not going to dwell on this, but I will explain a few things a little better. But Atterberg's test to figure out the cohesiveness or the binding energy, make sure we get that plasticity index high enough. We do, another thing we're doing is working on the moisture reabsorption. Okay, so there are things we can do to the mix that will actually help inhibit the reabsorption of moisture, which is very important for the long-term durability of the roads. These are various types of strength tests, which I'll explain in a minute. But there's Riley working in the SCM lab, and there we can do these kind of images you previously saw, chemical analysis and X-ray diffraction. And what X-ray diffraction does is it gives us the minerality of the clay. So here's an example. Again, this is pen or pit clay that we use, and this analysis number 2 here is what that minus 200 mesh fraction is actually comprised of. So that's your fines, and you can see it's mostly silt. Things like quartz and feldspars, carbonate minerals like calcite and dolomite, a bit of mica, and also some of these reactive clays like montmorillonite and illite. Okay, so it's roughly, this material is only a 1/3 actually reactive clay, okay, good clay. The rest is just dust makers unless you have the proper binding in place. If you have the proper binding material, then all the silt actually works in our favor. And it works in our favor because of it helps to densify. So that's why and the reason for the good size fraction distribution, because if you just have gravel and clay, if you have gravel, you have a lot of pore space. Okay? If you have gravel or coarse gravel, and then you have finer material and finer material all the way down to fine silts and then ultimately clays, you fill in every pore space. So we can get maximum density occurring. And when you get maximum density, then the clay is able to fill in the last little bits of pore space, and then you get that to cement up, and you end up with a very strong bearing strength and a very tough, durable road. Okay, so some of the tests we do. This is a typical CBR test where we mix the road material in here, and then we apply pressure to it. So this is a load frame, and it'll apply up to 10,000 pounds of pressure. The dial up here measures the pressure, and that's the proving ring, and it compresses with the pressure, and that gives us the extent of that. And this dial measures the penetration of the piston into the road material in there. The other type of test we've done a lot of are what we call unconfined compression tests. So we make these clay pucks, and that's why I passed those clay pucks around, and then we put them under extreme pressure until they fail. So we determine their maximum strength, and the reason for doing this is so we can manipulate the product and the way we compact and so on and so forth in order to maximize the binding strength. Okay, so we can test the different materials, different product adding, and different ways and means of compacting in this manner. So what I want to do at this point now is show you an actual one test on one puck. Okay, it will only take a minute for me to set it up, and then a minute to run the test, and you'll see what happens. But basically, we're going to jump into an experiment. This is Riley and Melanie ran this, and they filmed it for us. Okay, so there's two separate films. One is showing the puck, and the other is showing the compression dial, okay, the pressure. Now, what's already happened is the dial has gone around 8 times, so each one of these increments here, and each one of those increments roughly represents 1,000 psi. Okay, so we're currently sitting at about 7,800 psi, and there's your puck still sitting there. Okay, that's a 1 square inch piston. Okay, on the puck is the exact same pucks as what you're looking at there. So if that sounds like extreme pressure, it is. So when it reaches maximum bearing strength, then the dial will stop moving and the puck will start to break up. So as we get near the end, you'll actually see a crack forming over here in the puck. And that determines its maximum strength. Getting into this. Melanie's worried.
Sorry, it makes me like jump every time. It's coming, but.
So they're out of sync, but basically, you get the idea, okay? So what's happened here is it failed, okay, catastrophically, a little over 8,800 PSI, pounds per square inch. Now, put that in perspective, a car running over the road is roughly, puts a pressure of about 30 to 40 PSI, the same pressure as what you put in your tires. The large gravel trucks, maybe 110 PSI, okay? Household concrete fails on the normal standard concrete test of between 2,000 and 4,000 PSI. Average construction concrete will fail at about 7,500 PSI. This failed at 8,800 PSI. Now, don't go too far with that, because you can't make a direct comparison between this test and concrete cylinder, because the test is done a little bit differently. Okay, but just to put you in a kind of ballpark, okay, framework, and eventually we're going to make this out of cement and whatnot, and we'll actually do the direct comparison. But the point is, it's failing, and it's behaving almost like, well, in this particular case, okay, it's if we do significant compaction, okay, product is in there. This gives you an indication of the binding strength and power that is available in these reactive clays. That's the only thing you should take out of this, okay? Not that this is concrete or anything like that. It's not. But just so you understand, if we harness, okay, the available, okay, potential that's in there, okay, we have something that can line things up very, very strongly. The trick is in the construction and how we do this, and the product and the ways and means by which we catalyze this. Okay? And we're also things we're doing at Brandon University is working on transferring what we can do here in the lab into what you can do in the field. And that's why I say that, you know, as we go forward, I expect that we're going to see significant improvements in what we can do beyond what we can, the great roads that we already can build. Okay, so now I'll quickly take you through one of our road building, okay, exercises, and then my presentation will be done. Okay, so building a road, okay, an EarthZyme road, is the same as building any road. All good standard road building techniques and apply. Okay, so you all know what a typical gravel road looks like, with your crown, the wearing surface that is, the subbase, subgrade, and so on and so forth. Proper slope, okay, is important to keep the water off. And but what we deal with is the wearing surface, the crown, if you like. And the addition of 6 to 8 inches of a good A base with that good particle size distribution, with the high clay content of 25 to 30%. In fact, the best road we built is 32% of that clay fraction, meaning the minus 200 fraction, and that clay fraction must have a high cohesive clay content, true cohesive clay content. Okay, so first thing we do, you got to source the materials. Okay, so we're not used to dealing with clays like this, so we have to go out and find the appropriate clays, which means testing in the pits, and we do the particle size analysis, Adderberg's testing for plasticity and cohesiveness, binding and bearing strength tests that we do in the lab, and also CBR and combined compression strength tests that are done in the lab. Then we head off to the quarry, okay, and this is the Blue Star quarry, where they mix most of the material we've used. This is their typical normal A base, and this is the stuff they mix for us, using an A base plus the Pennerkit clay material. And that material, in this particular case, had 32% of the fines in it. So that's what we work with. Once we've mixed and we're satisfied that we're well mixed, then we do what we call Proctor tests. The Proctor test is to determine the optimum moisture content. And that's the moisture content at which you will get maximum densification and compaction during the construction process. So we need that number. Okay, and we'll get back to it. Next thing is to move all that material out to the road site. This is Laurie Road in Cornwallis in 2015, and there you can see the material is there in Wind Road. During this process, the road remains open, so there's no need to close the road, even though it says road's closed. That's because we're just about to start the main construction process. Okay? And just prior to the main construction, we do a moisture test on this material here. So we know what our optimum moisture content is, and it might be something like 9.5%. If you measure this, and let's say we're at 6%, then we want to, by the time we're done, we want to bring the moisture content up to optimum, or actually just below optimum. So if it's optimum is 9, we'll take it up to something less than about 8.5. So we've got to add 2.5 to 8% water. Calculate that in terms of, we know the tons of yards and tons of material that are out there. We calculate the liters of water required. Okay, it takes us to the next step. So in that particular case, it turns out we need 12,000 liters per half mile. Okay, so, and then we add the appropriate amount of the product from Cypher. In this case, it's about 35 to 40 liters of the EarthZyme product that we added to that 12,000 liters of water. Okay, now we've got to mix that into our windrow, and the way that's done is a grader will go along and take roughly 1/3 of that windrow, lay it down in the lift on the road. The water truck goes by and drops the 1/3 of its load. Okay, so now it has all the water and all the EarthZyme product in it. Then the grader will take that wetted material, move it to the other side of the road, put down the next lift, the water truck dumps its next third, the third lift dumps this final third of material. Now we have all the material and water in the road material. Okay, so so at this point, I'll just pause and tell you. Okay, so what is the EarthZyme product we're talking about? Okay, so it comprises of 3 main things here: surfactant, okay, which promotes wetting, ionic exchange, and densification. Okay, and in other words, a simple way of putting it is water and the ionic polymers into the road mix, and then helps get the water out. Okay, so water and product must go in, and then water out. Cationic polymers are those calcium, magnesium, iron, potassium, okay, that replace water in the bonding of clay particles, as I showed you in the previous slide. And then organic catalysts are added, which promotes the ionic exchange in the bonding process. Okay, so that's the product that goes in, and that's the way in which it's added to the road material. It's fairly simple and straightforward. Okay, so once we've added the product, what happens next is it gets rolled and mixed. So we roll it back and forth across the road 3 or 4 times, and you can see the graders are working in tandem. There's 2 graders working in tandem on this road, and they'll move it over here, they'll move it back, and come back. 3 or 4 times is enough to get everything thoroughly mixed. Okay, so that's very important. And then grader goes and shapes the road, and the first bit of packing, which was the wobblies, the pneumatic packing takes place. Okay. That is followed by then the steel drum roller, a nice heavy steel drum, 1 pass with the vibratory packer, and assembled without vibration. And then at this point you have a very solid road, densely packed, solid road. But there is one more step, and that's the surface seal. And the surface seal, all we do is water truck will go with just water or any leftover EarthZyme. You can throw it at this point. Wet the road, let it soak in for 10-15 minutes, and then you'll go with the wobby and pack that down, and do that a couple times. It gives you a good seal and final compaction on the surface there. And then now you've got a really good running surface, very durable at this point. Okay, so this takes place in 1 day. So the road shut down for 1 day, and from beginning to end of the process, 1 day. And then as soon as this last process is finished, you can open up the traffic again. In fact, at this point, the more traffic, the better, and the heavier the traffic, the better for these roads. Okay, and that's it. And then except for we do follow-up testing. So this is a nuclear densometer. Actually measures the density of the packing of the road material. That's Riley with his dynamic cone penetrometer, and that gives us a CBR, California bearing ratio. So it's just a measure of the bearing strength of the road. Okay, so And then, of course, we do actually dust monitoring and we watch the road conditions and we stay in touch with Cornwallis and other people. So we're regularly out there looking at the roads. Okay, so just to summarize, and this is the end of my presentation, I think there are 3 ingredients to a successful road build. One is the engineering and test work, the materials and the product is the second, third, and the final third is the construction. So all 3 of these need to come together, and if they come together and they're done properly, you get a really good road at the end of the day. So, and I'll just stop right there. This is the Curry's Landing Road, built in Cornwallis in 2015, and most interesting thing about this road is that although we like to achieve a point at which the maintenance is reduced to once yearly, and in fact, initially this was daily maintenance, okay, because of the heavy truck traffic that's on there. It serves about a half a dozen or more quarries, active quarries, 150 or more loaded trucks a day going on this huge dust problem and whatnot. But they've gone from down to, I'd say once a year, but in actual fact, the last 2 years, they haven't touched the road. And Heather's here, she can verify that there's been 0 maintenance on that road for the past 2 years, although we like to see that once a year. And the maintenance that normally is done once a year would be to scarify, a couple inches of the surface, just reshape, and then just roll it with the wobblies and then let the trucks do the rest of the back.